Okay, all right, so that's basically it for this question. Okay, so that's basically it for question number 5. Let me look at question number 6. Okay, so this one doesn't involve any calculation. It's kind of like a conceptual question. It says, the solubility product constants are usually specified for 25 degrees Celsius. How does the KSP value for a chemical compound depend on temperature? Let me hear your answer to this question. What do you think would be the effect of temperature on KSP? Any ideas? Okay, let me ask you this. Generally speaking, how does temperature affect solubility? Generally speaking, not, of course, in all cases, but in most cases, how does temperature affect the solubility of a compound in water, let's say? No ideas? Okay, at last, somebody says something. Let's see. Exactly. This is Mr. Powers. Okay, very good. So Mr. Powers says an increase in temperature will cause an increase in solubility. And that is generally true. There are some exceptions, right? But generally speaking, increase in temperature will result in an increase in solubility. So if that's true, then what effect does temperature have on the solubility product? Because remember, the solubility is different from the solubility product. Let me give an example. The simplest example I can think of is silver chloride, right? The KSP for silver chloride is equal to the solubility of silver chloride squared, right? So what effect will the increase in temperature have on the solubility product, the KSP value? Come on, folks, this should be too easy. Exactly, it will increase it too. And if you look at the formulas of the KSP as it relates to solubility for different compounds, it's always KSP is equal to something times S to the squared or S to the cube. It doesn't matter. If the solubility increases as a result of an increase in temperature, that means that the KSP value would increase as well. So to answer this question, KSP will increase with increasing temperature. That's pretty much all I would expect for you to, because the question didn't ask you to explain. So this should be sufficient with increasing temperature. This should be sufficient for you to answer this question, all right? Okay. So that's number 6. Now, number 7, I think I'm going to leave you to do that because number 7 is very similar to what we did earlier, right? So I'm going to leave you to do number 7 on your own. Number 7 is similar to, just in case you need some guidance, is similar to number 4 and number 3, right? So if you understood number 3 and number 4, then you should be able to do number 7, all right? In fact, hold on, let me see here. Oh, I just realized there's a B part. Okay, so we have not done, okay, all right, tell you what, let's do number 7. Because the A part you should be able to do, but the B part, We haven't done any questions like this. I don't think so. Anyway, so let me clear this. And let me scroll down. Number 7, all right? So number 7, calculate the molar solubility of lead 2 chromate. And it gives you the Ksp value. Okay, so let me hear what you have to say. What would you do first? Well, what would be the very first step in solving this problem? Okay, so create an ice table. Of course, we have to write down the equation. Pb2 plus CrO42 minus. So initially you're gonna have none of that. Then the change here would be plus S. So at equilibrium, you're gonna have S and S, which means that Ksp is equal to S squared. So this implies that S is equal to the square root of Ksp, which would be equal to square root of 1.8 times 10 to the minus 14, right? And let me do that on my calculator, 1.8 times 10 to the minus 14. Then I find the square root of that. And according to my calculation, this works out to be equal to 1.3 times 10 to the minus 7 m, all right? So that would be the solubility of lead 2 chromate in pure water. Now, the next question is asking for the molar solubility of lead 2 chromate in the presence of 0.020 m. So we did an example of that in the PowerPoints, right? And this is an example of a common ion effect because the common ion in this case would be the chromate ion. That's an ion in common with both the lead 2 chromate and the sodium chromate, right? Now the ice table that we would set up in this case, let me clear this first. The ice table that we would set up in this case will be slightly different. It's the same equation, but write the equation down, Pb CrO4 to form Pb2 plus CrO42 minus. Initially, you're going to have no lead 2 plus here, but here, initially you're going to have 0.020 m of the chromate ion, right? So the change here will be plus S and plus S again. At equilibrium, however, you're going to have S here, and you're going to have S plus 0.020 m, right? Now, the thing is that we're going to assume that S is much smaller compared to 0.020 m, right? Which means that this would approximate to be equal to 0.020 m. So when we plug those terms into the Ksp expression, we're going to end up with S multiplied by 0.020 m, which means that S will be equal to the Ksp divided by 0.020, and the Ksp was equal to, what was it again? Go back up here. 1.8 times 10 to the minus 14. So down here, we're going to put 1.8 times 10 to the minus 14 divided by 0.020, and we work this out. 1.8 times 10 to the minus 14 divided by 0.020. And according to my calculation, this works out to be equal to 9.0 times 10 to the minus 13 m, right? And that would be significantly smaller compared to what we calculated in the A part. If I remember correctly, the S that we calculated in the A part was equal to 1.34 times 10 to the something? I don't remember what it was. Can somebody remind me? For the A part, what was the solubility that we calculated for the A part? Oh, 1.3 times 10 to the 1.3 times 10 to the minus 7. Okay, so as you can see, the solubility that we just calculated in the B part is significantly smaller compared to the A part, and that's because of the presence of the common ion. The common ion presence shifts the equilibrium to the left and therefore reduces the solubility of the lead to chromate. All right, so that's basically how that is done. All right, any questions about this? Any questions? Any questions? Any questions? Okay, so let me clear this. And let me go back to the PowerPoint. And okay, so next topic we're going to discuss is the issue of complex ions being formed in solutions, all right? Now let's define what we mean by complex ions, and then we're going to see how equilibrium principles apply to the formation of these ions. Now, a complex ion is basically a metal ion which is surrounded by one or more molecules or ions, all right? So here's an example. The cobalt 2+ ion surrounded, well, not surrounded, but reacts with the 4 chloride ions here, and you end up with this here, where you're going to have the cobalt ion bonded to the 4 chloride ions, all right? So we call this a complex ion, okay? Now, complex ions are formed as a result of equations like these, where you have an equilibrium being set up. So therefore, you can write down an equilibrium expression for the formation of a complex ion. And the equilibrium constant in this expression is called the formation constant or the stability constant, right? So Kf in this case would be equal to the concentration of the cobalt complex here, cobalt chloride complex here, divided by the concentration of the cobalt ion, multiplied by the concentration of the chloride ion, raised to the 4th power, because of course you have a 4 here as a coefficient, right? So basically, as a result of this relationship, we can use the formation constant or the Kf value, stability constant, as a measure of how stable the complex ion is, right? Basically, the greater the value of Kf, the greater would be the stability of that complex, all right? And here is basically a photograph of the formation of the complex from the cobalt ions. So basically, the cobalt ions in water forms a complex ion. This is the formula for the complex ion. And then when you add chloride ions to it, the reaction changes the aqueous solution to a blue, from a pink aqueous solution to a blue aqueous solution, where the blue color is due to the formation of the complex ion, all right? And what you'll find typically is that when it comes to complex ions and their formation constants, these values, the Kf values, are typically very high, all right? As you can see in these examples. In fact, among these examples, I would say the lowest one, the smallest Kf value is 2.0 million, right? Times 10 to the 6. 2.0 times 10 to the 6. And that's at the low end in this list right here. It can go as high as 10 to the 16, as you can see in the case of the complex formed between the cadmium ion and the cyanide ion, all right? Or 10 to the 30 is even higher, right? 10 to the 41, the mercury cyanide complex ion, the Kf value for that is 2.5 times 10 to the 41. So basically, these complexes are very stable, right? Which means basically that if you have this system in equilibrium, the major concentration species that will be present would be the complex ion, and you'd have a relatively small amount of the other species on the left side of the equation, all right? And this idea of complex ions can be used to perform what is known as selective precipitation. And this is just basically showing you how to do that. Basically, selective precipitation is a way of selectively precipitating out different ions that may be present in a solution. So let's say you have a situation where all these ions are present in a solution. Then first you'd add HCl, and what that would do is precipitate out the silver chloride and the mercury 2 chloride. The silver chloride will precipitate out first because its Ksp value is lower, and therefore that will precipitate out first. And then the silver 2 chloride, I'm sorry, not silver, the mercury 1 chloride will precipitate out next, and then the lead 2 chloride would precipitate out next, and so on and so forth. So basically, you have to be careful when adding your precipitating reagents. Typically, you have to basically add them slowly, drop by drop, and then one precipitate will be formed, and then you can filter that out, and then you continue adding the others until basically all that can be precipitated out will disappear. The only thing that will be left in the solution are those ions that cannot be removed by precipitation, like potassium, sodium, and ammonium. You simply cannot remove those by precipitation, all right? So that's basically what we call selective precipitation. And this is just basically another diagram showing you basically the same thing, pretty much, all right? Okay, this is just showing you some tests for cations, flame test, indicating the presence of some ions present. Basically, the way this works is that you take a piece of nichrome wire, you dip it in your solution. Nichrome wire, by the way, is stable. It won't react with anything. So that's why we choose that. We stick it in the solution, and then we stick it in the Bunsen flame, and you end up with these different colors, which indicate the presence of different ions, right? So this lilac color would represent lithium being present. This yellow color indicates that gold is present, and so on and so forth, all right? Okay, and then this is just showing you some examples of precipitation reactions that occurs in nature. And this is basically showing you how the calcium carbonate responsible for the formation of an eggshell is formed. Basically, what happens is that there's a reaction of carbon dioxide and water to form carbonic acid, which undergoes a two-step dissociation process, which forms carbonate ions, and then the carbonate ions will react with calcium ions to form the calcium carbonate precipitate, all right? Okay, so that's basically it for this chapter. Let me see here, let me go back to the assignment here. Okay, we did number 8 already. Okay, can we do, you know something? I'm going to stop here for today, all right? So just to remind you that your test is this coming Wednesday. And that test will cover chapters 3 and 4, all right? So 3 is equilibrium and 4 is acids and bases, all right? Any questions? Any questions before I leave? Okay, let's see here. Oh, okay, thank you for saying that. I didn't realize that. But what Gilcrease was saying was that in problem number 5, I forgot to multiply the 4.35 times 10 to the minus 4 by raised to the 3. I forgot to multiply by 4. So make sure you make that correction, multiply by 4 to get the correct answer. All right? Any other questions? Okay, if there are no other questions, that's it. I'll see you guys on Wednesday.